Good afternoon, everyone. Welcome to another CAN seminar series. For this week, actually, I am the moderator here, and I guess in place of Dev Mishra, who's now I know my postdoc. He's in India, actually. He's been doing the seminar series. And it's my great pleasure to welcome actually one of our payment research engineers, civil engineers from Federal Highway Administration at Turner Fairbank Highway Research Center. I can probably say the name right.
Siva is good. Thank you.
Sivaneswaran.
Oh wow, that's perfect.
In short, Siva. We're very happy to have him here with us. Actually, he's coming from Turner, the Fairbank Highway Research Center. As I said, he's involved in conducting and coordinating research and payment design, payment performance modeling, payment structural evaluation, and most importantly, life cycle cost analysis, which is the title of this presentation, and life cycle assessment and payment management related topics. So he's there at the FHWA working since 2006. Before joining FHWA, Siva worked at the Washington State Department of Transportation for 12 years, and the last 5 years as the state payment management engineer. So at the Washington State DOT, Siva was involved with payment structural evaluation, payment management, and payment management related research. And his bachelor's degree in civil engineering is from University of Peradeniya, Sri Lanka.
So like
Master's and PhD from the University of Washington. So with that, I'd like to welcome Siva again to give us this.
Thank you very much, and it's truly a pleasure to be here. Thank you, Imad, for inviting, and thank you, Dev and Lori, for coordinating and scheduling this one. And good afternoon, everyone, again. So I just wanted to give an overview and a little bit in-depth use of probabilistic analysis as we use in life cycle cost analysis in general and specifically for payment type selection. I assume most of you are in payment engineering or civil engineering, so this is nothing new to you. But just want to give what we are promoting. We are providing as a best practice in making investment decisions for our infrastructure, which is basically supposed to last for a long time. And so again, the topic of the presentation is life cycle cost analysis. And just a brief presentation outline, just what is life cycle cost analysis, the definition, the 5-step process in conducting an LCCA, and what the state of the practice in terms of how state highway agencies are utilizing the life cycle cost analysis for decision-making process, and also to go a little bit in depth into probabilistic LCCA, and you will see as I go through this process why that's important, and then just provide some resources or references that may be useful to you in case you are interested in further understanding or further information on it. Okay, this is a standard definition. It first appeared at the T21. T21, Safety Law, MAP 21. These are the Reauthorization Act for the Highway Trust Fund. That's what the the state DOTs and used to build and maintain their payment network. This was the T21 came in the early part of the 20th century, and then the MAP 21 is the latest one. Both of them basically kept the same definition, which is basically saying it's a process for evaluating the total economic worth of a usable project segment by analyzing initial cost and discounted future cost, such as maintenance, user reconstruction, rehabilitation, restoring, and resurfacing cost over the life of the project segment. So there are, it's a mouthful, but basically what we are emphasizing is how long when you are designing a payment, how long do you think the payment should last? For all practical purposes, forever, right? I mean, we rarely, take the payment out of service. Maybe another 100 years, maybe technology might change, but it's supposed to last forever in there. So we don't want to make decision, even though that we may be designing for 20 years, 25 years in terms of traffic because of our, the inability to design and forecast, long period of time, but they were supposed to last for a long period of time. So the bottom line is that we don't want to make decisions based on initial cost alone. We want to consider the future maintenance, rehabilitation. And this is something that you do in your everyday life. I mean, when you are buying a car, you are not just going based on your initial cost. You are looking at, okay, what's the, the maintenance and repair cost of that car, and you are willing to pay a little bit more upfront if you think that it's a more reliable car, that you have less, repair and cost associated with that. So it's nothing new, basically, and then over the life of the project segment. But as I said, a life of a payment is, the project or how long we want it to last is really forever, but we cannot, when you have to set a period of your, the analysis so that you can begin to quantify that all your cost and the benefit within that analysis period. So we will come back to an analysis, a term called analysis period, which basically we say it's long enough that that is not going to impact the decision that you are making. So that's the key to it. So when we say life, we do really mean the life of the project, which is if we want it to be last forever. And LCCA, life cycle, it's an analytical tool to provide a cost comparison between two or more competing design alternatives, producing equivalent benefit for the project being analyzed. So this is some key differences in here. You all have, I mean, there are two economic analysis concepts that you might have heard about. One is the benefit cost analysis. The other one is the life cycle cost analysis. The life cycle cost analysis is a subset of benefit cost analysis. Benefit cost analysis is something where that you are comparing both the benefits and cost of a decision or of something that you are contemplating. But in the life cycle cost analysis, we are only comparing the cost, which means that we are assuming there are more than one alternative available, that you have decided you are going to build that project. All you are trying to determine is which is the most cost-effective alternative. Fundamental thing is that those alternatives, that the competing alternatives should be providing equivalent benefit or close enough benefit. So when you are thinking in terms of the concrete versus asphalt typically, or a steel bridge versus or a steel deck versus a concrete deck, basically we need to make sure that the service being provided to the traveling public are of similar in nature throughout the life of the project. So there are 5 steps to conducting a life cycle cost analysis. Again, so this is basically, some of the fundamental I wanted to capture. So what you want to do is, first thing what you want to do is, you want to establish the alternative. What are the feasible alternatives that provides you equivalent benefit for the project that you are considering? How many projects, alternatives should you have if you want to conduct a life cycle cost analysis? At least you need to have 2 alternatives, right? Because you are doing a comparison. If you have only one alternative, there's nothing to compare. You go with that one. So you need to have at least 2 alternatives. And once you have established the alternative, then as you all know that, okay, once you build the payment, you have to do periodic maintenance. and to maintain a level of acceptable level of service. So now what you have to do is you have to set the timing of those maintenance when they need to happen, maintenance or rehabilitation or reconstruction activities. Once you establish the timing of then they estimate the agency and user cost, step 4 for computer lifecycle cost, and step 5 the analyze the results. I will go through each one of them briefly right now. Okay, so establish the alternatives, the activities to ensure performance. So even though we are talking in terms of payment type selection or as it applies to payments, it's the same principle whether you are applying for bridges or tunnel or any project, any construction project, or even in your personal life, something you are trying to buy. So you are make sure that you have a set expectations of performance over the usable life of that project. And to achieve that one, you know that you have to initially purchase or initially construct or rehab or reconstruct that project. And then you are going to also have rehabilitation or maintenance activity to keep the level of service or the performance level above the acceptable level. And so that will determine your future rehabilitation and preservation activities timing. So these are so for each alternative, you select the alternative and then the initial or reconstruction activity, and then you have your future rehabilitation or preservation activities. So here's, once you establish that one, what you are going to do is you are going to establish the timing of those activities for each alternative. So you have there is a series of 3 actions happening. That's those arrows. So you have the initial arrow. That's where your initial action your initial action is right in here. And then you have some type of rehab because your performance is deteriorating. You want to maintain an above an acceptable level of service. And then you have another activity, and then it continues to deteriorate. So here is here's the initial activity, activity 1 and activity 2. This is what we call our analysis period. As I said earlier, basically, we don't, if we set an analysis period, it doesn't mean that we are going to take that payment out of service. It's going to continue to serve. But there's a balance between how, the further into the future that you go, the more uncertain you become about it. So you have to draw, strike a balance between how long you want to continue the analysis, even though recognizing that these assets are supposed to last for a long time. But at the same time, your uncertainty associated with everything, that's what we will be talking about in the probabilistic analysis, is going to increase. So you have to strike a balance, and the balance is basically what you want to do is you don't want that, knowing that this is an arbitrary analysis period. You don't want that analysis period, that period that you are considering all for your life cycle cost analysis, impacting the decision that you are making. Okay, so this will come into play. So we want to say, okay, if you typical analysis period is like right now the present practice is 40 to 50 years. If you use a 40-year versus 50-year analysis period, and if your alternative, the preferred alternative, changes over, then your analysis period is not long enough, because it is an arbitrary threshold that the cutoff point that we are choosing, because we don't want our ability to predict into the future becomes diminished as you go further further out. But the rule of thumb is basically you want to have at least one major activity within that analysis period. So long enough to capture the differences between the alternative is what you are governing criteria for selecting an analysis period. Once you have established the alternatives and the timing of the activities, the next thing is to estimate the agency and user cost. So the first thing is to estimate the agency cost. Agency cost will include overhead cost, preliminary engineering, construction cost, as well as any right-of-way acquisition for the initial construction, and then all the future rehabilitation and maintenance activities. But being a cost comparison between two alternatives, one of the beautiful things about life cycle cost analysis for selecting the most, the preferred alternative is very often you will end up with two alternatives where a lot of the costs are common between those alternatives. So, for example, if you are, having a realignment project, your right-of-way costs are going to be there for regardless of what alternative that you are choosing. Anything that's common between, the common for all the alternatives that you are analyzing, you don't have to consider into your analysis. The reason is because this is not a cost estimation tool. It's a cost comparison tool, which is the most preferred alternative. So if there's one or more costs that are common to all the alternative that you are using, it's going to be washed out, right? Are you following me? So that simplifies, because so you don't want to unnecessarily complicate your analysis by including cost or factors that is going to be a washout when you are actually making the actual comparison and making that selection of which is the most cost effective. So any cost that is different between those two alternatives, any one of the alternatives that you are comparing, you need to include in the in the cost comparison. And then the second part is estimating the user cost. Normally, we are not talking about the normal operating condition user cost. Again, when you are thinking about either the bridge life cycle cost analysis or the payment life cycle cost analysis, we are not talking about the normal operating condition user cost. What would be the normal operating condition user cost? It could be due to congestion, because our capacity is not there even under normal operating condition. It could be vehicle operating cost because the payment surface or the bridge surface roughness. But what we are saying is we are going to provide the similar level of service, similar benefits, because those are the benefits between the alternatives. So they must be equivalent before even we bring them into competitive alternative. So the only core user cost that we are considering in here are the cost that occurring during work zone condition. The reason that we need to consider that work zone user cost in life cycle cost analysis is because, as you know, if you are comparing concrete versus asphalt, you have different number of rehab activities that you need for each of those alternatives. So if you have a concrete pavement, maybe you might have to go and do a diamond grinding in year 25, and maybe some crack slab replacement in year 35. Okay, so those are the two work zones. Maybe some joint sealant in year 10 or 15. On the other hand, if you are an asphalt pavement, maybe you might need an overlay in year 12, another inlay in year 25. So you have different number of activities and different type of activities which is going to require you to put a work zone. And so they are going to be different between those two alternatives that you are comparing, two or more alternatives. They need to be captured. And when you think in terms of user cost, once you put a work zone where you are taking the lane survey as well as the reduced speed, you introduce queuing, so you have a delay cost as well as the vehicle operating cost. And so basically you impact all those traffic impact into what we call in a monetary terms of what we call user cost. We treat the user cost and the agency cost separately and keep it separately throughout the analysis and also throughout the decision-making process, because these are two different pots of money. Agency cost is hard money that the agency has to spend. User cost is money that the user is losing because of the work zone or the interruption that happened. It's time value of money. But they are different pots of money. We want to account for them, but we don't want to combine them. So once you establish the agency cost and user cost for the initial construction and the subsequent rehab or rehab maintenance activities, what you do is you do a cash flow diagram. I think you all are familiar with cash flow diagram. So you have your initial activity, and then you have the preservation activity, and for each preservation activity, then you have the associated user cost. Every time you go and put a work zone to do some maintenance or preservation activity, then you are going to have a user cost associated with them. And then, maybe you may have a major rehab activity, and then, so associated work zone user cost. And this is where your cutoff point is. Okay? So what we account is at this point, there is still service life, the value left in the payment. And so it's just like, your car, you buy a car in 20 years, there is still value left in that car. And so when you are, computing, your life cycle cost for that, the maintenance of the vehicle, at the end of the 20-year period where you are going to trade in, it becomes a positive cost for, it's a value for you. And so that's what we are calling it, salvage or remaining value. Basically, that's the amount, the amount of the remaining value of that payment or the structure or the bridge structure when you terminate your analysis at that analysis period. Similarly, this is a controversial point. I mean, because, okay, you can say that, okay, you have a value, for the physical asset, but do you have a salvage or remaining value for the user cost? Because they have already endured. I mean, but if you do because you went and did a major activity in here, they stand to benefit, reap that benefit into the future without having a work zone. So you need to account for that by taking a salvage, remaining value for that user cost. Once you get develop the cash flow diagram, then what you are computing is a net present value of all your initial construction cost and future future activities that in your cash flow diagram. So in life cycle cost analysis or any benefit cost analysis, you can work in terms of two types of dollars. One is the real dollars, one is the nominal dollars. The real dollars is where that a ton of asphalt cost maybe $400 today. It's going to cost $400. Okay, I think asphalt is a bad example because there's a lot of volatility on the asphalt price. But let's say any commodity, you have an escalation. There's an inflation component to all product that you buy. You remove the inflation part of the cost increase, then you are dealing in terms of real dollars or constant dollars. That means something that costs $400 today still costs $400 tomorrow or 10 years in the future, which means that we are basically effectively removing the inflation of the product. So either you could work in terms of real or constant dollars, or what you call is nominal dollars, which means you inflate it. So something that costs $400 might cost $500 in 10 years down the road. Now, what you need to do is, if you are using in terms of inflated dollars, then because you have, these costs are occurring at different point in times, you need to bring them into a common basis, which is normally taken as today's dollars or present dollars. And so if you add the inflation, then when you are you bring it back to today's dollars, you have to remove the inflation back. So why add the inflation and then bringing back, you have to remove the inflation, that inflation component again. So the best practice is to use constant or the real dollars and use today's price to do your life cycle cost analysis. Okay? But still, there's an interest component to your time value of money. So when you are, so if you have $100 today, if I loan you $100 today, I would expect you to pay me back not just $100, but $100 plus interest 10 years down the road. Okay, so that's the interest component of that today, the value, time value of money. So what we are saying is that, okay, there's an inflation component and the interest component. You take the inflation out of the interest part component, then you end up with the discount rate, which is the real dollar or the constant dollar, but that has a time value of money, and that is represented by the discount rate. So this something that you when you are dealing in terms of real dollars, something that you cost $400 is going to cost $400 in 10 years down the road, right? But you don't have to keep $400 in the bank to buy that product 10 years down the road. You need to keep only $350 in the bank because it's going to earn the interest up to that 10-year period. That's what the discount rate is. So any cost that's occurring into the future needs to be discounted to bring to the present dollar value. That's what this discount, the D or the discount rate is. And so basically this is just a mathematical expression. You have your activity occurring at nth year, and you discount it by the 1 plus D and the factor of 1 plus D plus NK, which is the present value factor, and then you bring that one, all expenses that you have occurring at different time to a common dollar, which is the present dollar or today's dollar. And the fifth step in this process is, once you have computed the net present value for each of the alternative, now you have the important part of making the decision. Okay, so you have, we compared the agency costs. I said that, you had to compute them separately. You have the user cost. So how do the agency costs compare? How do the user costs compare? And can the trade-off be made between the user costs? So what we recommend in terms of payment type selection or payment, or bridge, is that, you have your alternatives, you have the agency cost, life cycle cost in terms of net present value for each of the alternative, and the same for the user cost. Now you are making the decision as to if there may be a case that the lowest costing alternative, also in terms of agency cost, you may be lucky that that's also the one that cost lowest user cost. Then you have a clear winner in that case. But very often what will happen is some of your lower agency cost alternative might end up costing, resulting in a higher user cost. In that case, you might be able to say, okay, now I'm willing to, as an agency, willing to spend $1 more to save $5 of user cost. So those are some of the decisions that the agency can consider in identifying the preferred alternative. So this is a kind of a quick run because I wanted to make it brief because most of you probably are familiar with life cycle cost analysis. You have used it in one form or the other. Just wanted to give a basic introduction on what are the 5 steps in the process and what do we recommend in terms of applying to payments or bridge projects. A few slides on the state of the practice, but there was a 2013 survey that was done in terms of, this is with respect to payment type selection. Payment type selection is a process. I think I'm making some assumption that some of you are familiar with what I mean by payment type selection. Because when an agency is ready to either reconstruct or major rehabilitation or new construction project, they have typically 2 types of materials to use: asphalt and concrete. And so they have different performance characteristics, different cost, initial and future cost, and future rehabilitation activities. And what the agency is trying to determine is which product they are going to use to construct that project. That's what the payment type selection is. And since there are competing industries, they want to make sure that the agency considers, give them both the equal opportunity and makes the decision based on the most cost-effective solution for that particular project. So that's what the payment type selection is. And so there was a South Carolina DOT made a survey last year in terms of what the state of the practice. Out of the 23 states responding, about 78% of the states use life cycle cost analysis for payment type selection. And this is kind of misleading because I went and looked at which are the 5 states that said they don't use. They do use, but they don't use it in a formal way. So on either larger projects or they have, on an as-needed basis. And these are just highlights of few of the issues that you want to find out what the state of the practice. So, do they include user cost or not in making their selection or the determination? About 2/3 or maybe about 60% of them they do. On the other hand, how many of them are using probabilistic analysis? About 2/3 of them don't use probabilistic analysis. And again, I said that the analysis period, we really want to look at the life of the project. The life of the project is really for our transportation assets. It's forever, but we need to strike a balance between how long we want to accumulate cost and do the analysis versus making the decision based that's unbiased. And so this is kind of a slide. Basically, somewhere between 35 to 50 years is the standard analysis period that most agencies are using, which is not uncommon, and which is basically what what's the recommended practices. And then how often that LCCA procedure, because the inputs, the performance, the material, everything is changing, and how often they update their inputs as well as the procedure. And so I mean most of them within the last 5 every 5 years or within the last 5 years they have made some update to that both the procedure and input. Real quickly, one of the the challenges in life cycle cost analysis and life cycle assessment that you will be doing is they are very data intensive, and you are looking in terms of a long time horizon. So there are significant uncertainties and variability associated with the input that you are using to make those decisions, make those, run the analysis. But as soon as, you recognize that there are significant variability, significant uncertainty, how do you account for them? You have to, if you are trying to make a decision with uncertain and highly variable data. And so unless you account for those uncertainty and the variability and make a decision that trumps the uncertainty over, the variability that's associated with that analysis, you will be, you won't have the confidence in making that decision. So, but just real quickly, there are two approaches available in conducting life cycle cost analysis. One is the deterministic and the one is the probabilistic. The probabilistic analysis is the one where you will be able to directly account for the uncertainty and variability associated with the input that you are using to make that decision. In terms of, what the state of the practice, I think I have already, shown the 2013 statistics. About two-thirds, the two-thirds of the states are still not, utilizing the probabilistic analysis. So why again, we are emphasizing, the probabilistic analysis. Many analytical model treat, inputs as discrete fixed values, but most inputs are uncertain. Economic models used in typical LCCA is not different. Again, if you take in terms of LCCA, if you take the initial agency cost, you have the market condition, competition, bid cost, quantity, construction duration. I mean, there are a lot of input that goes into determining the initial agency cost. None of it is known with 100% certainty. There is a significant amount of variability and uncertainty associated. In terms of future agency cost, your performance, your payment technology improvements, agency policy changes that is happening, so you might be designing for 20-year payment design life. All of a sudden you change it to 25-year, 30-year payment design life. You were using ASTO 93 guide, now you are using MEPDG. So the policy changes, the engineering changes. And so basically only certainty that there is significant amount of uncertainty associated with all the input that you have. This is a classical example. What it shows is, this is from California, almost 10,000 projects. Between 1993-94 fiscal year to 2008-2009, what it shows is basically based on the number of bidders versus the engineer's estimate. So the engineer's estimate versus number of bidders. So engineer's estimate is what the agency compute before they go out for bid. And based on the number of bidders, you can see how much of a variable, which is expected, but the amount of variability, variability is significant. If you have only one bidder, typically it has been almost 26% higher than the engineering estimate. But if you have, close to 6 or 7, then you are into 14 to 15% lower than engineer's estimate. But what we don't know is, we don't know when you go out for bid, how many bidders are going to be there, how many bids you are going to get. So this is one, just classical, uncertainty that you have when you are making this decision, before you let it out for bid. You are doing the life cycle cost analysis, making this estimate, and say, okay, this is the most preferred alternative. But you don't, these are the uncertainties that exist at the time, and how do you account for them? And the probabilistic analysis is a need that you need to, there's significant uncertainty, significant variability. So why states are still using deterministic analysis? These are some of the examples. It's easy to understand. It's much easier to do analysis based on discrete input. You have discrete numbers, you plug it into the equation, and you have the single answer. And you can use best guess from past experience, data, the data set or expert opinion. And its analysis results are easy to interpret. If you are running a probabilistic analysis, what do you end up with? You have a distribution, right? And if you have two alternative, then you have two distribution. Much difficult to interpret than if you have two, concrete cost 2 million, asphalt cost 2.5 million, you have the answer. So challenges are, again, what is the challenges with doing the deterministic analysis? It's without, in the absence of reliability, you really, the outcome may be misunderstood that, okay, this is the fixed number. The probabilistic analysis or the risk analysis came into play mainly in transportation sector because of the big Houston project, Boston project, sorry. Started out as a $2 billion project, turned into a $14 billion? Boston big, 14 billion. Yeah. So the uncertainty, that will come to haunt you if you don't, because when you give 2 billion as the estimate, everybody will consider that, okay, that's the fixed number. That's basically the single answer to that problem. And when you already knew as an engineer, you knew there are contingencies, there are so much uncertainties. If these condition materializes, you are going to encounter cost increase. But if you don't communicate that, then you risk that number being taken as the ultimate, the final answer. But actually, when I have done a lot of, the life cycle cost analysis for payment, my worry was, I know that I have to make a large number of assumptions. Okay, and if what I want is, I still have to make the decision. I still have to tell my boss, okay, this is the most preferred alternative. But if I don't have a feel for if one or more of my assumptions are not valid, is the answer going to change? If I don't have, if I keep worrying about that, then I don't feel confident in the information that I need to provide to my manager. So that's the main reason in conducting a probabilistic analysis, because it gives you the confidence in communicating the information that you are trying to communicate. But there are significant challenges in probabilistic analysis. It's data intensive, computation intensive. Results are not as straightforward to interpret as deterministic analysis. And again, this is one of the main things is that, when you are trying to communicate to your managers, they don't want to look at two different graphs and two different probability distributions. They want, okay, tell me the answer. But one of the beautiful things is that life cycle SCCA for payment type selection, or any of these type of like life cycle assessment, when we are comparing two competing alternatives, it lends well to probabilistic analysis, because it's not a cost estimation tool. I think, again, I have already mentioned that one. Basically, in terms of life cycle cost analysis, it's not the individual cost that you are interested in, it's the difference in cost, right? It's the difference in cost, because if you take the difference in cost, but you're like, okay, let's say something costs $100, another thing costs $110. When you are trying to compare that, what you are trying to really compare? The difference in cost, right? So what that does is, when you look at considering in terms of difference in cost, you have, let's say you are comparing two different alternatives. You are actually, your output that you are trying to look at is the difference in cost. It collapses those two distribution into a single distribution, right? The single distribution is much easier to compare and contrast than trying to work with two different distributions. So life cycle cost analysis, lends well to that one in there. And this is one of the other key, like, when you are running an LCCA, you might have, you might be working in terms of 50 to 100 different inputs. Traffic, user, the time value of money. But when you are running when you do the probabilistic analysis, you will find there are only a handful of items that do really control the difference in cost. What is, there are only a handful of items that's going to be key to making that determination. And probabilistic analysis lets you identify those key inputs so that you can further research them to better estimate them or reduce the uncertainty in them so that you can arrive at a more confident determination. So basically, I think some of you might have seen real cost software. It basically implements this probabilistic analysis for life cycle cost analysis and make it a much easier to analyze within the Microsoft Excel framework. Again, some few comments. It's basically we wanted to develop in Microsoft Excel because most of you already are familiar with the Microsoft Excel and comfortable with it. So it makes it much easier for, there's no learning curve in using this analysis tool. Some highlights on, what are the features that are available. I just want to, I know that running late on that, want to make a quick case, want to illustrate this probabilistic analysis through a quick case study. This is a case study in Washington State. It's a 12-mile section of a roadway being reconstructed. There are three alternatives they consider: crack and seating, existing PCCP overlay, HMA full depth, and PCCP full depth. And I am only going to, for the sake of time, only going to concentrate only on these two alternatives. And these are some of the inputs that goes into each of those alternatives. So this is the probabilistic input for HME alternative. As you can see that there are a large amount, this is just a handful of, the input that are needed to that analysis and how we have treated them in terms of probabilistic characterization. Initial construction cost, initial construction work zone duration, and here is the PCC alternative. And what we have is, so this is the difference in distribution. Okay, so I said we had a, so we have an HME alternative and PCC alternative. Those are the two alternatives that we are comparing. And basically what this graph shows is the difference in life cycle cost between those two alternatives, which is the agency cost HME and PCC alternative, which is the present value, life cycle cost, present value of life cycle cost between the HME and PCC alternative. Okay, so here's your graph. Okay, so this is in thousands of dollars. So basically this is minus 1.5 million and 1 million. So what can you say looking at this graph? Okay, so what can you say? So you can say basically here's the zero line. So that means if you fall in this side of it, the HME alternative, because HME minus PCC or the HME alternative is the most cost effective alternative, right? Because that's the cheaper, right? Are you following me? If you are on this side, then that's the the concrete is cheaper, right? So what we can say in here is that's 80% of the HME alternative agency cost is lower than PCC alternative 80% of the time. That's a pretty good probability, right? But you can say 80% probability is a very good probability, right? So you would go ahead and say, okay, for this particular project, HMA is the most preferred alternative. But remember that you made quite a bit of assumption here. If you look at it in, these are the input that went into your analysis, and this came from your data, but they are still significant amount of variability and uncertainty associated with them, right? So what you want to, one thing that you want to do is, okay, 80% is a very good probability, so I am comfortable with that one. But one thing I am still wondering is, I made a lot of assumption. I made various distribution, various answers. Are there any changes that could change this probability? You see what I'm saying? So what you have is, what you will get is the tornado graph or tornado chart is what will help you get to look at which key input variable could basically influence the distribution. Okay, so right now we have 80% of the probability that HMA is cheaper, and if you look at it, even though that we had more than 15, 20 inputs that were characterized as uncertain or variable input, when you look at the tornado graph, there are only a handful of them. Actually, in this case, only about 2 or 3 of them that even show up on the chart. What this says is, okay, these are the 2 key input variables that can basically control the position of that graph. So what I am doing in here is, okay, so what this is the most sensitive input change. If you change the mean value of HMA bit cost by 1 standard deviation, you are going to shift the different distribution by 0.67 standard deviation. So what the initial assumption was, we said, okay, $80 is the cost with the $20 standard deviation, and if you happen to, depending on the location, you happen to the asphalt is going to cost $100, what is going to happen? Now what we have in here. So this is our original graph. Now this is our just change in one variable, HMA bit cost, and this is where you end up in here. Now what conclusion can you make? This is our original graph, right? And so now both alternatives are equally competitive, right? There's a 50% chance because you are right at the $0 is at the 50 percentile mark. So what you want to do in here is, so what this helps you do is that you identify the key variable, key inputs, uncertain input that could really shift the decision from what you are, from the one alternative to the other. And now you want to make sure that you have a better handle on those key inputs. So if you were using your statewide average for your asphalt price, and you run this analysis and you identify these are the 2 key inputs, what you want to do? You want is, okay, depending on the project location, you stratify by project location. Then you reduce the uncertainty, increase your confidence interval in the input. So rather than trying to do that for all the variables, uncertain variable, that may or may not have an impact on your final answer, this helps you identify those key variables that can impact the decision that you are trying to make, so that you can focus on those selected input to make your payment of selection with much better confidence. That's what this probabilistic analysis helps. On the other hand, if you use, for example, the activity service life, which has a much smaller bar, much smaller sensitivity, look at where you end up with before and after when you change your standard deviation, to change the service life by one standard deviation, hardly any change in the decision that you are trying to make. So that's what the tornado graph is. But so some few key points in the tornado, it's you have variability in your data and uncertainty associated with the future prediction and the performance and the input that you are trying to estimate throughout the life of the project. And tornado charts help in identifying those few, the input variable that could significantly impact the decision being made from the many in the LCCA model. That's the key thing there. The total uncertainty that you have include both system inherent variability and uncertainty due to lack of knowledge. The system inherent variability is something that you cannot reduce. So if you have a subgrade, it's variable. You can make more measurements, but still variable. But on the other hand, it's if you are talking in terms of what's the bid price is going if you go the ton of asphalt. If you take the statewide average versus the location that your project is, then you do the further research and you can reduce the uncertainty associated with that bid price. So there are certain variables where you can reduce the uncertainty by further research, but there is a system inherent variability that you cannot reduce it. But both of them you need to quantify and capture them. And again, so some of the few other caveat in here that you cannot any variable that you did not treat it as probabilistic variable, you don't have any information as to whether they are significant or not. Because if you don't treat them as a probabilistic variable, then you don't really have whether they are significant or not. So you really, if you are if you think that something that is uncertain or that's variable, then you do want to consider that as a probabilistic variable. This is another tool technique or statistical technique that you can use is that tail analysis. But because of the time constraint, I'm going to just cut it short in here. But basically, what that is, once you identify which project, which alternative is preferred alternative, then you still have uncertainty associated with that, that specific alternative, and now what your challenge is to see, okay, what is driving that uncertainty? Now you are looking at the extreme tail and understand what you need to do to minimize that uncertainty. So that's, and there are some, these are some of the resources that basically the best thing is to, Google FHWG LCCA, and you will end up with, a large number of our reports and other resources that you will be able to access them. I think I took the whole 1 hour in there. Sorry about that. But any question or? Okay.
Years ago, user costs frequently were only accounted for, like triggering user costs use 15% of that value. You're using the full market value of user costs.
Yes, we are, but we are not adding them. We want, some agencies are discounting by 15%, 20%. What we are saying is compute it. If you don't compute it, we don't even know what the magnitude of it. Then it's mostly to use to whether you can change the work zone configuration, work zone hours, the number of lanes that you want to take. So, because as you know, the traffic flow is very highly non-linear as far as the demand versus capacity. So the real cost of that, basically, this demand capacity formula gives you the ability to quantify them and consider them either whether you want to incentivize in terms of early completion bonuses, or change it from nighttime to daytime to nighttime construction, 55-hour closer. So we are asking them to compute it so that you have a magnitude and start adjusting your work zone closer strategies to minimize them. That we are not really saying, okay, you should factor, combine it with the agency cost in making the decision. But there are some agencies are doing, I think Georgia at one time said, okay, they have a matrix and say they are going to add a weighing factor of 20% to user cost in terms of selecting the alternative. Any?
In Illinois, we do life cycle, in payment type selection, they do a life cycle cost analysis. The maintenance scenarios are, quote, consensus values, okay?
Right. Mm-hmm.
I've watched this happen over the years. The consensus values don't change. I've looked at projects that are several years old, and I've looked back at what should have been done, and it hasn't been done. So, the idea of these so-called maintenance scenarios, that's very important. A lot of times, you just sway a decision very quickly.
Exactly. That's why, those are, that's why we encourage probabilistic analysis so that there are significant variation in the amount of maintenance you need and amount of, how much it costs, but we still need to make that decision. But if you can at least account for them in a probabilistic manner, and still one of the alternative comes on top, as being the preferred alternative, at least you can say that, okay, these are all accounted for, and still there is a clear winner. If not, then there are, go into the third set of factors, could be alternate bidding or many other factors. So this is just a one aspect or one component in the payment type selection process in there. This is not, there's an engineering, there's an economical, and then the third aspect is, everything else combined where they are going to make the determination, okay, this is, route continuity, experience, the local experience in dealing with one or the other type of material. And so Washington, like for example, we have a 3-step process. First step is engineering. Is it engineering feasible? The next step is economically feasible. And the next step is, okay, everything else.
That report looks fairly recently. 703
Which one? 703, yeah.
Type selection.
Right, yes.
Is that something you guys worked on?
No, it's actually that one ARA worked on it actually. ARA worked on it, yeah. But it basically references our resources in there. And
that software associated with that?
No, software we provide, but that's the software that NCHRP recommends. Right. They basically recommend.
Is that available on your website?
Yes. But the NCHRP report is available on the NCHRP TRB website. So if you Google it, you will find that report. Software is available on our website. Right. Right. It's basically an Excel worksheet with just a user interface attached to it. Okay. Thank you very much. Thank you.